Okay, so your programming test 1, the result has been released. So you can look at the announcement I made last night, the result, and also the feedback. You can take a look. If you've got any doubts, more than welcome to discuss with you during my office hour. Please come. And if you believe there might be some mistake on the grading, you can also submit some regrading requests. But do notice there's some deadline for submitting the request. Submit, and then I'll ask the TA to look into it. If there's anything that's worth our change, the TA will bring to my attention, and I'll decide. Okay, so please follow the procedure and avoid emailing me. Usually it's not that effective to resolve any grading issue. So we'll do that systematically. Okay. And for your written test number 1, the TAs are busy grading the manual question right now. So by the end of Friday, I'm going to give you the result. If earlier, I'll make it earlier for written test 1 that you took last Thursday. Your lab number 3 has been released. This lab here, I wouldn't really discuss that much in the class. That one is more like going over the tutorial of TLA Plus, just to see how you can actually do some temporal logic formula, some verification, some simple one, using critical region, which you learned about in the operating system course. I think that can bring in some context about mission critical, because critical region is really the region you want to protect concurrent accesses, right? You want to have a disciplined way to do it. I can discuss maybe the solution once the deadline is passed, but for now, you guys just gotta go over the documents. It's pretty self-contained. If you got any trouble following any part, you're also welcome to drop by. I can also discuss with you. Okay, that's about lab number 3. As usual, I'll still highlight some solution with you, maybe after the submission deadline. And your programming test 2. Okay, I just want to bring us attention to here. Your fellow student is very kind to let me know. On the lab number 3 instruction there, I definitely mistakenly put the programming test 2 there. I'll make sure I fix it, right? No confusion. So programming test 2 will still be held on the same schedule date, which will be March 20th during your scheduled lab time. So this week here, we're pretty much free, but I will give you the guide about programming test number 2. It's going to be more like a combination of some lab 2, post condition, and maybe lab 3, a little bit about the critical region kind of a temporal formula. It'll be a combination of both. Okay, I'll try to make it a little bit more straightforward this time, okay, to help everybody. But you still got to study, of course. Okay, I'll talk about it when I release the guide. You can expect the guide to be released maybe Wednesday or Thursday the latest. Okay, and you can study that. For your last test, which will be written test number 2, is going to be also going to cover mainly about the LTL that we cover after written test 1 coverage. I will also confirm the coverage pretty soon. Okay, but we're gonna cover some more sophisticated stuff in the coming 3 or 4 lectures, just to see how we can nest the formula, and then possibly we can go a little bit into the program verification topic. We'll see how that goes. Okay, we'll go, no rush. So if you want me to slow down, whenever, just let me know. And for the exam, you guys know, right? It's April 10th. All right, it's pretty early, but we can still schedule some review session to help you, right? We'll try to do 1 or 2 before the exam. All right, any question about the course? All right, awesome. All right, let's now do a very quick recap. Okay, before that, my office hour, as usual, nothing changed. And also, you can also reach out to Andy if you got any question about the lab, right? Always there to help. Quick recap, and then we'll continue. So last time, we dived definitely much deeper into the semantics rather than syntax of the LTL formula. Especially, we talk about something called model satisfaction. We'll dive into it again, just by using more complicated formula. Let's just review very quickly about model satisfaction. The way you define model satisfaction is by using path satisfaction as part of it, its definition. Okay? So if you're given some states, usually the model itself, which is a label transition system, will be quite clear in the context. You don't really have to mention that again and again. You don't have to. So given the states, and then we say the state will satisfy certain LTL formula if and only if. So there's a universal quantification right at the front. You guys got to remember. We're going to consider every possible path pi, which will start with S, which is the states. And then we want to say every such pi is going to have the path satisfaction with respect to phi. The reason that we have to emphasize about this outer universal quantification is because when we want to nest about temporal operator, which we'll see today, you're going to get, for example, like a triple quantification. That's something definitely a more sophisticated case to consider nested quantification, which we'll see today. But the way you try to prove or disapprove different quantification expression, the principle will just be the same. We're just going to review as an example. Okay, that's something we'll do today, and also into Wednesday's lecture. All right, so that's the formal definition for model satisfaction. Okay, again, given all the pi, starting with S, you want to make sure you got the path satisfaction with respect to phi. Right? Just remember that definition. Of course, in the exam, you can also feel free to put this definition there on the data sheets. Right? By the way, so exam, you will be allowed to have a one-sided data sheets. It can be handwritten, it can be computer type. So you guys can start preparing if you want to. You can put whatever you like on the sheets.
For the handwritten, is there a specific font?
No, really?
Font?
What I usually like to say is no magnifier should be allowed in the exam, right? So that means the font size cannot be too small. How about 10? That should be the minimum. Okay, yeah. You shouldn't really try to put the whole course into the data sheet. That's not a good sign. Right? You want to put just the ones you cannot remember. For example, if I were you, I might just put some complicated post-condition pattern from maybe Lab 2 solution in there, just in case I need something like that. Right? You can put whatever you like, no constraint. You can also feel free to collaborate with your fellow students about making the data sheets together. That's also fine. Okay. All right, so let's go back to model satisfaction. So given that it's a universal quantification, how do we prove and disapprove? If you want to prove it for model satisfaction, you got to consider every path. That's the principle. And if you want to disprove it, you just need a single witness path. Guys, be careful. When I say witness here, when you want to disprove model satisfaction, you want a witness path, not a witness states. Okay, witness path. That's something you got to keep in mind. All right. Of course, for the formula that's kind of contained inside the model satisfaction, sometimes you might need further some witness states. It's possible, right? But at the model satisfaction level, you don't need any witness states. All right, and we did an example here. You guys can definitely dive into the details. We basically try to compare model versus path satisfaction. All you got to do is look at the left-hand side. The left-hand side, we got states. That means model satisfaction. So you guys can look at the example that we talked about just for propositional formula. That should be the most straightforward ones, in which case you only look at the initial states in the path. Okay. And then we talk about the next operator over here. The next operator, by definition, is going to be pi to the power of 2, meaning that rather than looking at the initial state, you look at the second states. That's by definition, right, the next states. All right, so we talk about here path satisfaction versus model satisfaction, right? You can look at the details from the recording. It's all there. Okay? You can review that. Of course, this part here is going to be covered in your written test number 2. Okay? It's going to be, may not be a bad idea to start reviewing. All right, and then we talk about the different binary temporal operators. We talk about the global operator. Global operator is very one extreme. You basically insist for every, if you only talk about path satisfaction, if you got some path over here, you're insisting that every state in here must satisfy that particular property. How do you prove it? You got to show that every state, or all the reachable states in that path, will satisfy the formula. How do you disprove it? Show a witness states. All right, given that path. All right, and that's the model satisfaction version for the global, right, for the global operator. So you can also refer to the details that we spoke about last time. Okay, very quickly. Let's say when you talk about model satisfaction for global operator, how do you prove it? You have to make sure you go over all the possible paths starting with S0. For each such path, you want to make sure all the states in that particular path will satisfy the formula that you're referring to, right? It's like a nested quantification idea, 2 levels. How do you disprove it? Well, you have to somehow choose a witness path, and for that particular witness path, you have to choose a witness states that will violate the property, right? You basically got 2 existential to really disprove it, right? It's all consistent with the proving strategy that we spoke about earlier in the math review. Okay. All right, any questions so far? Okay. And once you start reviewing, I would suggest, since all the notes template, the blank ones are available to you, the best way for you to practice is to really print out or download the empty pages into your tablets and then practice each one of them. Of course, in the actual test or exam, the format will be very similar. I might just give you a different LTS, Could be more transition there, and could be more path patterns for you to consider. But you just have to make sure you're considering either path satisfaction or model satisfaction. And do you want to prove it or disprove it, right? It's always this decision making you have to perform smoothly during the test. All right. And I believe that's the last example we did, right? The future operator. So what we did, what we managed to finish last time was about the path satisfaction for the future operator. Let's say given a particular path, the future operator is really the other extreme as opposed to the global operator. You want to make sure at least one state is going to satisfy the property phi, right? So that's something we spoke about. So if, how do you prove it? To prove the future operator for the path satisfaction, you got to give a witness state to prove it. Show that this is the state that's going to satisfy phi. How do you disprove it? It's going to require a little bit more work. You want to show that there's no such future states ever in that infinite path. So for all the reachable states for this particular pi, it simply does not satisfy the phi. All right? So that's about the path satisfaction. And now we're going to move on to model satisfaction for the future operator. Right? That's the next one. Just always remember, for each operator, we always talk about path and then model satisfaction, just to compare the both, right? But they kind of related to each other. All right, any question? All right, let's do more example then. So this, the idea for today would be, we're going to talk about a final one with a single temporal operator, just about the future operator for model satisfaction. And then we're going to talk about how we can nest temporal operators together. We don't really have to, well, in theory, there are infinite number of ways for you to really, I shouldn't say infinite, there are many ways, how about that? There are many ways for you to nest different operators. But we're only going to talk about some important patterns, just to show you the principle about whenever you're given a new pattern for nesting the temporal operator, how are you supposed to derive its meaning based on the definition? Of course, for definitions, you can always put on your data sheets during the exam. And then you just got to work out exactly what a new pattern means according to the definition. I'll show you that technique. That's my job, right, during the lecture. But I'll get to here in just one moment. Let's do one more example about the path satisfaction. Okay, one more. All right. So you can see for all these formula over here, we got S0 on the left-hand side. There's a state, right? Just remind ourselves very quickly, right? You can see S0 here is actually a valid state. S0 is in the capital S, right? Capital S is going to contain S0, S1, S2, right? So it's a valid state. And then we want to now consider all the paths starting from S0, right? In this case, S0. And then we want to make sure that particular path will satisfy the formula. And the formula could be either this, or this, or this, or this, or this. Let's preview ourselves very quickly. If you somehow intuitively decide this path, this model satisfaction here should be true, what does that mean? That means you're going to show that for every such pi, there is a witness state that's going to show that this phi here can be established. All right? How do you disprove it? The way to disprove it would be you have to give a witness path. From that witness path, you're going to show that every possible state is not going to satisfy phi. There's no way. There's no such future states. All right? Yeah, I didn't really write this down, but if you really want to maybe review it, you can just watch a recording. Okay. All right, let's now take a look. And we're still including these trivial cases, right? Every state will always satisfy true and always not satisfy false. So these two will still be true, right? For the same reason. You can easily prove them. So these two are simply just true over here. All right, and then we're now going to talk about, let's say, the third one here. So this one we are basically say, for all the possible paths starting from S0, all such paths, at some point in the future, we're going to have this particular proposition established. That's what we're saying. Okay? Do you think this should be true or false? True? Okay, if you believe that's true, you gotta justify that, right? And to justify that, you gotta argue that for every possible path starting from S0, there will be a future point that's gonna satisfy this formula. right? Let me guide you a little bit. If you guys are still struggling a little bit about this, it's normal, but you just gotta practice, okay? It turns out this guy here is true. But how do we prove it? Yeah, Adrian.
Well, if you look at the three states, none of them satisfy both P and R at the same time. So because no state satisfies it, no path can satisfy it.
Mm-hmm.
None of them has both P and R at
Yeah,
the same time.
that means every one of them will satisfy this formula here, right? Yeah, exactly, sure. Yeah, absolutely. That's another way to say it, but let me just say it in a more general way, but you can definitely simplify that as what you said. I'm going to do both, okay? Okay, the result here is going to be true, and then let me tell you what you got to say, okay? So all paths starting from S0 have a future states satisfying. And here, I'm just going to apply De Morgan, okay? Not P or not R. Let's start with that. That one is consistent with our proof strategy, all right? However, as Adrian pointed out, this particular LTS over here is like a special one for this formula here. Because if you think about not P or not R, this one here does satisfy not R, because R is not listed. And also, this one here satisfied not P, because P is not listed there. And also, for this one here, you can think about not P is not there, and also not Q is not there. So it definitely will satisfy not P. Right? So that means for this particular formula here, it's going to satisfy all the states. That means there's always a future states for doesn't matter which path you choose. So we can easily use this property here to say that this, what we are trying to prove, is actually valid. Okay. So that's the simplification we can make. So this is the case. Because all states S0, S1, S2 satisfy not P or not R. In that way, we can always find the future states, which can be either S0, S1, or S2. Doesn't matter which path we choose. Right? It's more like a special case for this property here. All right, question? But if you want to be a little bit more conservative, you can feel free to actually go back to, if you go back to some earlier example discussion, you can try the following. For example, you might say for path S0, S1, S1, S0, S0, S1, this particular cycle here, because S0, for example, satisfy this property. So it's the future states that satisfy the property. You can argue that way and try for a different pattern. That's also fine. But this one here is more applicable to this particular special case. Okay, you can do either one. All right, how about this one here? We're saying that for every for every path, eventually we're going to satisfy R. True? Agree? Okay, let's see. Okay, for this one here, if you believe that, then we're going to argue that for every possible path, right? So what we do is we can say all paths starting from S0 have a future states satisfying R. And how can we argue about it, right? What you can say is as follows, right? This one here, we're still using a similar pattern. You just got to observe, right? From S0 itself, by the way, does not really satisfy R. So that cannot be the future states, of course. However, from S0 over here, if you want to proceed further, you will either go to S1 or you will go to S2. No way around. In that way, you can see either we go to S1 or S2. S1 and S2 individually will satisfy R. So that can be the future states. Right? Okay? I'm going to write it down here. Okay, what I would say is over here, in all such paths, S1 or S2 is reachable, either one. And both of them satisfy the R. Satisfy R. So either one, either way, they can just be the, sorry about the blocking here. Okay. So all of them, both of them can just be either one of them, depending on which path you're talking about, they can be used as a witness states. Okay. Alrighty, final one. How about here? So we're saying that false. Okay, we're saying that all possible paths starting with S0, there's got to be at least one state that will satisfy Q and R. If you believe that's false, what should you give to me, by the way? Should you give me a witness path, or should you give me a witness states? Path, right? Since we talk about model satisfaction. All right? All right, your fellow student judgment was right, but let's write it down. Okay, this one turns out to be false. And what we gotta give is a witness path. Okay, I'll give that to you right away. But of course, you guys also need to know how to figure that out. So it can be S0, S2, and then S2. Basically, we're saying we just go S0, S2, and then S2, this particular path. And this path here is no way to have a future state that's going to satisfy both Q and R. Because for here, you can see when we go from S0 over here, S0 there, we know that not R. So it does not satisfy R. And also, once you get stuck into S2, it does not satisfy Q, right? So there's no way to satisfy them both. No way. There's no such future states. So in your actual answer, let's say to the written test, or maybe in the exam, especially the exam, so we will be a little bit more flexible in terms of the format you can present the witness path. I think even here, right, I can simply just write down the witness path, and then I would say this particular state is not going to satisfy this, and this state here is not going to satisfy that. That'll be obvious enough for us to see why it's a witness. Okay. Okay, let me see if I can make it closer to you. Oh, sorry. Yeah, if you cannot see the notes, maybe I'll post it later, so you can also see that. All right, any question? John?
If it was like Q and P, would that
You mean here? Change to Q and P?
Yes.
Okay. We can try. We have space. So S0, and then we say Q and P. Okay, so here, so we're saying that there should be states. Oh, sorry, I forgot to put the future. Okay, like that. Okay, if we put a future over here, that means all the paths must eventually satisfy Q and P. Eventually, actually this one will be true, isn't it? Because S0, oh actually no, Q and P, yeah, exactly. S0 here is going to be the starting states for every possible path. In that way, in this initial state, Q and P already satisfy. So that can be the future state for the witness for every path, all right? Nice question, but this turned out to be a simpler one. Okay. So what I would justify is you can say all paths starting with S0. S0 satisfy Q and P right away. That means S0 is already that future state we can used as a witness. Okay, good. It's a nice addition to the example. All right, so that would be kind of the last example that we're going to do just for a single temporal operator. So what we're going to do now will be we're going to see how we can nest the temporal operator. Ah, go ahead.
Sir, if you go from S0 to S2, it's going into a loop, and it's not satisfying Q and P here. So how is this statement true?
Okay, let me see. We're still talking about this one here, right? Okay, good. So in order to show this one here, we had to show that for every path, then there's a future state that's going to satisfy Q and P. So we know that every path is going to start with S0. No way around. But S0 itself already satisfies Q and P. So that one is satisfied right away.
Okay, so if the state satisfies the condition itself,
Right away, then it's also considered. Yeah, let me show you why. There's a nice question here. I will show you by definition, right? Okay, that one requires me to go back there. Okay, let me show you very quickly. That's about 2 lectures ago. If you look at the definition for the future operator over here, you can say we say I larger than or equal to 1. So the 1 here tells you that's in the very initial state that can satisfy the formula right away. That's why. Okay, good. Yeah. Yeah, guys, please keep it a little bit lower, please. Thank you. Appreciate that. Don't worry about discussing it. Just a little bit lower. Thank you. All right, let's now go a little bit further. Okay. So I want to go, for the very first one, we're going to see some nested like a temporal operator. I want to go very slowly for the very first one. Once you see the technique, we can go a little bit faster when we see another pattern. Okay. So the first one we're going to see, let me show you the slides. We're now done with slide number 39. Okay, that one's done. What we want to do is how we can nest the different temporal operators. Okay, so this is the one we want to see what that means exactly. Okay. And let me now give you some intuitive sketch, right? So we can discuss that. That's kind of the thinking process you want to have. So what we're talking about here is slide 40. Okay. So what I want to talk about, let's talk about model satisfaction, which will include path satisfaction anyway. So we will talk about, let's say you got some states, and then model satisfaction, and then I got a future operator, and then the global operator, and then some phi. Let's just apply what you did in written test number 1. When you see this one here, why don't we try to draw the parse tree right away, right? That can also help interpreting the formula. And this one here, you can see we start from the phi, and then overall, this one is going to be applied first. You always go from the rightmost over here is going to be applied first. And then you go for this one here. All right. So this part here is going to be this. And then we got G and phi. And then we got F over here. Whatever G phi is, we're going to apply that with F. So that means F is right here. Okay, you can think about this implicit parenthesis over here. Implicit. Doesn't really exist in the tree, but it's just implicit. Okay, and a little bit further. You can think about this subtree over here or subformula. This subformula represent a property to be, you can say established or satisfied. Let's say satisfied. To be satisfied in the future. And when I say in the future, I really meant it's going to be connected to this future operator, right? So future operator is going to say in the future, we want to have this particular subformula satisfied to be evaluated true, right? So I think the parse tree is kind of nice for you to see the order of evaluation. Okay, let me do a little bit more, and then we'll talk about some visual sketch about what this really means. Okay, so let's remind ourselves. So this part over here, because we talk about the states here, so that should be model satisfaction. Model satisfaction. That means we got to consider all the paths, starting with S. Starting with S. Okay, and then this one here, let me just use, okay. The phi right here can be any arbitrary LTL formula that can be further derived. Okay. Arbitrary LTL formula. Okay. before I visually sketch what this really means, and then we'll see the formal definition, anybody would like to try? Intuitively, how would you describe what this formula really means? Before I point to you, Adrian, anybody would like to try? I'd like you to try, but I'll just see anybody want to try. Go ahead.
So in a future state, eventually it should hold forever.
Okay, at some point in the future, maybe starting from that future point or so, some property is going to hold continuously, something like that, right? Okay, let's now visualize it. What your fellow students say is pretty much accurate. Let's say, for example, of course, we're going to consider all such pi. We're going to consider all the path, right? Let's say in general, a path that will start from S. Right, you can see the S over here is really matching the S right here. So we talk about infinite path, like that. Okay, that's a path. And let's start with the future operator. The future operator simply says at some point in the future, does not need to be S, it could be, but doesn't need to be. Okay, so I'm going to say at some point in the future, you can think about some future states. It may be very close to S or maybe very distant from S. As long as there's such a state, that'll be fine. From there, we actually want, starting from that point, starting from that, including that particular state, you can say maybe here this is element I. Right, we can say that. So I, you can say starting from Si in the path, like ith components in the path. And then from there, we're going to say every state from there, the phi is going to be satisfied. So every state, including here, 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 every state, they're all going to satisfy phi. And this will correspond to the G part. That's how I can visualize it. Basically, in order to really prove this one, given some pi, you have to find that future point. And starting from that future point, including itself, all the states subsequent to it must satisfy phi. Doesn't matter how distant the future state might be. You just got to find it. Okay. All right, so that's a visual sketch to give you some intuition, right? And then we're going to make it a little bit more formal. And then we'll do some example. All right, any question about this? We're good? Okay. And let's now move on to this right here, right? So we're talking about this nesting here. So we got future and we got global. By the way, later on, we can also try global and then future. Since they are nested in different order, so they are not necessarily meaning the same thing, not really, but they are a very common pattern, which we'll get into a little bit later. But let's now focus on this one here first, okay? And this is just the informal meaning that I mentioned earlier. Okay, let's just look at that once more. So we are saying that each path, so that's a for all, starting with S is such that eventually is the future operator, which we know is about there exists, right? Some future point. And then it's going to hold continuously. That one there is more about a global operator, right? That's a for all. So you can see we got 1, 2, and 3. We got 3 nested quantification. Well, it's not too bad, right? We're going to talk about proving and disproving strategy on this page. Once we see the pattern, we're going to look at it together, and then we're going to just do some example. Okay, that'll be the flow. And each path over here, you can think about that one there is really about the model satisfaction. Model satisfaction. All right, right here. Okay. Now, how do we formulate it? Right, let me just go directly to the answer, right? But of course, the formula is going to look a little bit complicated for the first time, but you got to get used to it. Okay. Let's start with this part over here about every path starting with S. That one's easy. So what I would do is I'm going to say for every pi, and pi starts with S. Okay, that's the outermost level. We'll start with this. And then whatever that's here is going to be the property for the for all. And we want to say that eventually there should be a future point right here. So that means there exists, I can use I as a dummy variable. And we know that for future operator, it's basically like that, right? For a future operator, there should be a future point. I can say I larger than or equal to 1. And, right, so this part here is about a future operator, eventually, at some point. Starting from that point, this phi over here is going to hold continuously. Okay, there's going to be a third level. And let me just put another parenthesis over here just to show to you that's the third level over here. Okay, watch out here. So here we're going to say something like, we're going to reuse the I, okay, the same dummy variable, to really show to you however G is going to be satisfied is relative to the future point you have chosen as a witness. That's something we'll see later when we see the example. So here we're going to say for every, for every, let me introduce another dummy variable here. J larger than or equal to I. I'm going to visualize it, don't worry. Let's just write it down. And then that one implies, finally, the property, which is phi here. We're going to say that, finally, phi to the power of j pass satisfaction phi. That's the entire definition. Of course, I try to break it down into different lines, just easier for you to see the structure. All right. So think about right here, that's the pass satisfaction. Okay. And right here, you can think about right here, we talk about S here, FG 5, if and only if, right? And this one here is the model satisfaction, right? Right. And for our discussion about proving or disproving strategy, let's now do a little bit of annotation here. Okay. You can think about this one here. Let's say this is star. Okay, I'll put star. Star just applied to this particular universal quantification. Okay. And then I'm going to put another star star. Star star. That one there is just to say I want to apply to the existential quantification. Okay. And finally, I got this universal, the third level. Let me say star star star. By the way, the star is not part of the syntax. I want to use it so it's easier for us to keep track. First of all, let me pause. Is there any question or unclarity about this formula here? Yeah, go ahead.
Why is I greater than 1? That just because of...
Okay, sure. There's a more basic question here, but it's okay. I greater than or equal to 1 is the definition for like a future operator. Okay, let me show you again. Not S1 in the sense that it's the first element in the path, yes. But for that one, let me refer you very quickly, now that I'm already going back. Your fellow student question was, why should I be larger than or equal to 1? Right? It's because if you look at the definition, sorry, bear with me. If you look at the definition for future operator right here. Okay, future operator. So there exists an I larger than or equal to 1. Cannot be 0 because pi to the power of 0 is undefined. Cannot be 0. Okay, yeah. Okay, let me just fast forward to where we are. There we go. Right, any other question? That's not something that's not clear about this formulation here. So what we have done, two things. I want to just mention that. Because in the exam or in the written test, you might be given some nesting that we didn't exactly discuss in the class, but you know the technique about how to derive its formal meaning. So you will be able to answer questions related to the new nesting. Number one, whenever you're given some nesting over here, you may just want to draw the parse tree first of all, just to see what's the order of evaluation, number one. Number two, once you see the order of evaluation, try to see if you are able to draw something like this, just to see exactly how the formula is going to be applied, how the phi is going to be satisfied, right? Number three, you got to go with the definition about the outer level model satisfaction. You got to consider all the pi. This part here is always the same, right? Always no-brainer, just write it down. And however many the quantification is going to be here, and whatever they are, it really depends on the operator you're using and also how many operators you have in the nesting, right? So that's something you want to watch out as well. And of course, the final part here, whatever dummy variable you might be needed, is going to be the exponent for the path satisfaction. That's also always fixed. Okay, one more thing to say. You really want to, let me just write it out and then I'll mention that. Final point. Let's now visualize this once more. It will be a little bit more elaborate than this one here, but pretty much the same diagram. I'm going to use the dummy variable, just put it into context. If I got my pi here, which starts with state S, right? Again, the S here and the S here, also the S here and the S over here, right? They are the same S states. Okay, that's a path starting from S. Of course, we're going to argue for all such paths, but I'm just using some representative one. We're saying that at some future point I, so the I here really corresponds to the I right here. All right, starting from that future point, including I itself. That's why you see J larger than or equal to I, right? So you can think about the J here could be I itself, or the J here could be I plus 1, or the J here can be I plus 2, and etc. All such J. We insist that the phi should be satisfied. So that means the phi should be satisfied here, the phi should be satisfied here, should be satisfied here, all throughout. Okay? That's another way for you to understand the formula, more visually. All right. Any question? Before we see the example, which of course has to do with either prove or disapprove the pattern, why don't we take a look at how we can prove it or how we can disprove it? Okay. Okay, let's go directly. Okay, if you got any question, you can stop me, right? You basically have to handle each of the quantification one by one about proving it or disproving it. That's what you're going to do. We'll go from outermost into the innermost. So let's go with the first one here. How do I prove about universal quantification? You got to consider all the possible paths, right? So number one, we're going to say, we're going to consider all paths starting at S. That's how you prove it, right? You got to make sure all the path is going to satisfy this property here. But what's really this property? We're going to continue with the strategy. Okay, step number one, consider all the path. Step number two, we're going to handle the existential quantification, which to prove it is easy. You're just going to find one witness, right? You want to find a witness I, because we say there exists I. You want to find that future point. You want to find, for every pi you're talking about, find that future point first. Okay, that's how you handle the middle level quantification. And finally, how do we handle that innermost universal quantification? We have to make sure for whatever I that we chose for that particular pi, every value, every j starting from I, every point from there onwards satisfy the phi. All right. So here we're going to say each states at index I plus 1, I plus 2, and etc. all the way towards infinity. Of course, the states might repeat themselves in the actual path. That's okay. You know, you just got to find out reachable states starting from that point. will satisfy phi. All right, so that's a proof strategy, right? You can see it's very logical. We just go with the logical quantification. If you got a different nesting, you just have to change the strategy accordingly, depending on which operator you're talking about. Okay, some very quick annotation for you. So, okay, not yet. Maybe for the disproving part. All right. All right. Any question about proving it? We good? How do we disprove it? Well, we still go from outermost to innermost. You want to think about if I want to disprove the whole thing, I need to say I want to disprove this one here by finding a witness. I need to disprove this by showing that not every possible I is going to violate this property. And how do I show that this is violated? You're going to give a witness for that. Right? Go with that order. You just have to make sure you understand very well about proving and disproving universal versus existential. That's really the basic that we review in the math review lecture. Okay, let's now do this one here. So we still start with the outermost. But now to really disprove the universal quantification, we want to find a witness pi. Find or supply. Find a witness pi. Witness pi, of course, that one should start. That path should really start with S. All right. So this part here is really to disprove the path satisfaction. Okay. Let me write it down here. So this part over here is really about to disproving the path satisfaction. Okay, just this part here. And then step number 2, for that particular witness pi, we want to show that there is no such point. For all the point that can be a future point, this one here is simply not possible, basically. Okay. So now for step number 2. And for step number 2, we want to disprove basically about the future operator. Let me write it down first, and I'll write it down precisely. So for step number 2 over here, it's basically going to disproving the future operator, right? You can see the future operator. So what we do is try to disprove the model satisfaction, try to disprove the future, and try to disprove the global, right? That's in that particular order. Right, so what should we do in step number 2? You want to show that for all possible states, that can be the future state for all such I, basically, okay? So I want to say for all possible future states. Possible future states at indices, basically starting from 1, 2, 3, 4, all the way through. 1, 2, 3, all the way. Okay, and then finally, you want to say for all such I, there's no such J, really. Sorry, for all such I, there is some J that's going to violate the property. Okay, I write it down here. So that would be the third one. And the third one here is going to disprove the global operator. Okay, I'll write down the third step more carefully so you will see how the connection is. Okay, so this one here is going to disproving the global operator, right? So you can see the order goes like model satisfaction, future operator, and then global operator. Okay, the third step. When I say relative to the I, indices I equals. Okay, so just notice that we got I here. Okay, let me just put it down here. Indices I equals. Okay, and the final step would be with respect to each I. because we want to disprove the universal quantification, we're going to choose a violation case as a witness. There is a J such that J may be larger than or equal to I. For example, if I choose the I to be this one here, in that way, I just gotta give you, if I is here, and then I just gotta choose maybe some J here relative to it, and then not phi is the case, right? To satisfy the property. And pi to the power j not satisfy the phi. Of course, we're going to see example about that. The third step looks a little bit trickier, but it's really logical over here. Let me recap very quickly. Okay? To disprove it, it seems to be more sophisticated. We first have to disprove the universal quantification for path satisfaction. Choose a witness path. And then to disprove this, we're going to say for all such possible I, this will be invalid. How do we disprove this? You're going to choose such a j relative to the I that we spoke about, right? You got to choose the I first and then choose a relative j. Once you choose a relative j, you show that j here cannot satisfy the phi. Okay. So before Wednesday, you just want to look at these two, look at this pattern over here, and then look at how we prove and disprove. Right? It's really important. Okay, good. All right, any question? Okay. And I think the next step will be to do some example here, but I would suggest we take a very short break by taking attendance, and then after some break, we can do the example together. All right? So let me pause. Okay, two more things. So on the slides, so I think we are basically done about defining this defining formally about this pattern here. But of course, I spoke about many other things also that can help you get intuition. You can also refer to it. Proving, disproving, we also went over the answer with you, right before the break. All right. So we can go over some examples. So my plan would be we can go over this example here quickly, and then you guys can look at that for one moment and can tell me what the answer should be. Okay? Take some moment to decide. And then after that, I want to do one more interesting exercise to kind of ask you, and then I'll go over answer with you. And that'll be it for today. Okay? Let's focus on one by one. Okay, right here. How about this? Just for the sake of brushing up your mind, because we took some break, right? If you actually want to, check for model satisfaction intuitively, you want to make sure consider all the possible paths starting from S. In this case, it will be S0. Okay, just starting state. Of course, you can try later. If I change all the S0 here into S2, what's going to be the answer, right? That's something for you. So we're going to consider all the paths starting from S, and then for all such paths, are we able to find a starting states from which onwards you're going to get the property all satisfied, never being violated again. All right? That's basically what you're going to do. Okay? Let's do one by one. And of course, the property that we are talking about, the first one is actually this property here. The second one is this property here. And the third one is this property here, right? We got these three properties. Let's go one by one. All right, for this one here, do you think that should be true or false? Take one moment. Take one moment. It's okay. I heard true. That's fine. Don't forget, the really important point, I can tell you in some way for this pattern here, you may want to focus more on this global here. At some point, global should be true, even though that some point does not need to be initial point. It could be some point from distant from the initial point. But it's got to be true at some point. Okay. One more moment. You guys can take some time to think about, right? In some way, if you believe that it's false, then the rest will be easy. Just give me a witness, right? Farad, go ahead. True or false?
False.
Give me a witness.
S0, S1, S0, S1. That path will always have S0.
Pretty great. Okay, pretty spot on. Nice. Okay, that's exactly the model answer I have on my notes as well. Very good. Okay, so here is false, and one witness path could be, for example, we basically want to falsify just this part. That's something we are trying to figure out. Okay, so this will be false first of all, and the witness we're gonna find witness path. So the witness is somehow going to show that there is no such future point, starting from which R will just be continuously false, continuously true. Let me write it down first. There is no such a future point starting from which GR is true. Right, this one is more like a comment, right? So you can just use that to verify the answer. But let me give you the witness path, which Farris correctly said what it should be. The witness path would be basically go S0, S1, S0, S1, and etc. Basically, we're going for this loop. S0, S1, S0, S1. We never go to either here or never go to here. We never, right? It's basically this loop here. It's a valid path. And that one there, you can see that S0 can never be avoided. Can never be avoided. But R is not satisfied in S0. So that's a problem. Since there's no such a future point where onwards you will just get R satisfied because S0 is always involved. So there's no way. Okay. So once you give the witness path, you just have to give some explanation to show us you really understand that how that witness path is going to disprove it. Okay. Very nice. All right, so that's the first one. The main insight is really about for this infinite path, you just cannot get away from S0. If S0 only occurred in certain prefix, but it never happened again, in that case, maybe you're fine to find a future point just beyond that. But in this case, no way around. S0 is always there because it's alternating. All right, what about the second one here?
False.
Aha, give me a witness path.
S0, S2, and then it keeps on looping S2.
Okay, you guys, okay, pretty good. Okay, this one here, guys, in case you haven't found it, that's okay. You just gotta practice, but this one here is nice. So here, I'm gonna say the witness is going to be, let's say, S0, S2, S2, and onwards, right here, right? You can see that once we get to S2 over here, we just get stuck. In that way, none of P or Q is satisfied. No way. There's no such future point. Okay? If you choose the S0 to be the future point, that's a problem because S2 doesn't satisfy this. If you choose the S2 itself as the future point, also you'll be even worse because it's not satisfied right away. Okay? Okay, so here you can say S2 over here does not satisfy P or Q because you can see that that one there only satisfies R, not P and not Q is implicit. Okay, so there's no such future point. So there is no such future point after which P or Q is satisfied. All right. Okay, very good. What about, oh, question? Go ahead.
I just wanted to ask if we could do S0, S1, and S2 since it lands back to S2.
Uh-huh.
Is that a valid witness path?
Yeah, you will be fine too. If the witness path is actually S0, S1, and then S2, that's also fine. Yeah, because it doesn't matter if you choose this one to be the future state, you will still run into this guy here.
And it will keep looping.
Exactly, yeah. Exactly. Because this property here about G here is very strong. It's saying that from that point onward, it should always be satisfied. Okay. All right. All right, guys, final one. True? Okay. Well, this one here, simply because, well, to really show that it's true, you somehow want to consider all the paths, right? You got to go to this strategy over here about proving it, right? You got to consider all the paths. And for all such paths, there's always a future point starting from which all the states subsequent to it will satisfy this, right? That's what you do. However, there's a special case because P or R is already satisfied by every state that's reachable. All right? So this one here is actually true. So what you got to say is P or R is satisfied by all states. So for all paths starting from S0 we can simply choose S0 as the future point. And from that future point onwards, including itself, for example, if you choose this one future point, everything is going to satisfy P or R, for example, right? If you choose different path, all the state is going to satisfy that. So global operator over here is definitely going to satisfy. Okay. So it's not too bad, right? Of course, you want to be careful. Well, you got to make sure you learn about the principle. And if I modify the graph a little bit, you got maybe the patterns you got to consider will be different, right? When it's true, you got to consider all the possibility. When it is false, you got to give the proper witness. All right, exercise for you. You can change maybe from S0 over here into S2. Okay, give it a try. Okay, I want to talk about one more thing, and then that'll be enough for today. Okay, and then we'll talk about another pattern next time. Okay, I want to post some exercise over here that you guys can think about. Okay, I think this one will be nice to also review a little bit about whether a predicate is actually stronger or like a formula is a stronger or the weaker one. Okay, I'll put it right here. Okay, so let me give you formula number one. Let me put it this way. Formula number one and formula number two. So this one here is G phi. This one here will be F G phi, which we just have been speaking about, right? Let's say we got these two. And then I got some multiple choice for you. Number one, how about three choices? F1 implies F2. F2 implies F1. Number three, you can say F1 if and only if F2. Okay, choose the most accurate one. Okay, think about it, right? And you got to justify it, right? So that's a question, right? So think about in the exam or in the written test, this could be part one about making a choice. And part two will be to justify it, right? Let's just go on with part one. Ferris, part one, which option?
F1 implies F2.
You mean option one?
Yeah.
So F2 is stronger than F1, so it would be F2 implies F1.
So Ferris, you think there should be one, you think there should be two. Okay? One thing to say, okay, just before I tell you the answer. When you say implies, it's really about stronger and weaker. if you are able to justify that P implies Q. Okay, P can be any formula, Q can be any formula, right? Of course, here formula can itself be some propositional logic, could be practical logic, or could be LTL, the same, right? If I say P implies Q, I'm really saying the following. If I say this particular implication can be proved to be true, I'm saying the set of satisfying value for P should be a proper subset or subset of the set of satisfying value for Q. I'll write it down. This one tells me that the set of satisfying values of P is a subset of that of Q. More intuitively, I'm saying less value can satisfy P because it's stronger. It's more like a stronger filter to filter out the value. And Q is weaker, so it can allow more values to be contained within. Okay? And when I say subset over here, right? So it's more like this relation. However, sometimes you might be able to show that it's not just a subset, it could be a proper subset. Okay? If P cannot be equivalent to Q, that means we don't allow that equal over here. Let's say if we don't allow that, we should be able to find a value, let's call that V. Okay, let me write a little bit better. V over here. And V is actually going to be within the Q, but it's not within the P. Right? So V should really satisfy Q, but does not satisfy P. That, number one, satisfies Q, but does not satisfy P. Somehow P is strictly stronger. Okay, it's a proper subset. Okay. Okay, recap. When you only talk about implication over here, as you guys learned back in 1090, it's only a subset relation, which will include the possibility of equal. So we are saying that if we say that P and Q over here cannot be equivalent to each other, in that case, you should be able to find a witness over here that shows that there is at least one value that's going to satisfy the weaker one, but it does not satisfy the stronger one. It's more like a background. And we're going to need this idea again once we get to the program verification lecture, which will happen maybe in about 1 or 2 weeks. Okay. All right, guys. Anybody want to contribute answer for part 1? Okay, we got for 1, we got for 2 as well. Yeah, Adrian.
I think it's number 1.
Okay, go. Okay, sure. Good enough. Yeah, don't worry. Thank you. Okay, you change your mind to 1? Okay, no problem. Okay, yeah. Okay, it turns out you guys are good. The collective wisdom actually work. Okay, so it's 1. All right, but we're going to justify that. Okay. Okay, that's correct. All right. They are not equivalent. So what we do is let's now first of all let's write it down. So I'm saying the following. If I say I have a model that satisfies G phi, that always imply the same model is going to satisfy at some future states G phi, but not vice versa. Which means if I say given this, does that imply that? No, not in general. Okay. Not vice versa. Okay, I'm going to show you exactly how to think of it visually. Okay, let's think about what's happening here. If I say my model all the paths starting from S, all the states already satisfy phi. So that means the initial states can already be chosen as the future states. So that can automatically prove this one here. On the other hand, if I try to prove this way here, how can I choose a future state? I can choose a future state that's not necessarily in the initial states, in which case it will not satisfy global. It requires some insight into this formula here, right? So what I just said is more like an insight into the visual justification. But let's now take a look. Okay, let me do one more. Okay. So if you think about right here, okay, let's now draw some diagram to help us over here. You're saying that at some point in the, let's say at some point in the future, let's say you start with S, and then you're claiming that some point in the future, this can be the future point. That's not necessarily just the starting state S. This could be some future states. And starting from that future states and onwards, I have basically G phi satisfied. And before that future states, I actually got not phi. So this is a totally valid path or system or model where we satisfy this. Right? That's exactly what we said earlier before the break. You can convince yourself. So this is a valid one. However, given this particular model here, is it going to satisfy G phi? Is it? No, because right here, that's exactly the witness you can choose, right? So that means satisfying this does not really mean you can satisfy that. May not be. Okay, that's an intuition. So I'm going to just apply one more time the diagram here and show to you how to understand that. And what you guys got to do is to apply the definition for these two formula formally and see if you can prove or disprove it. Right? That's your exercise. Right? Let me just draw the diagram and then we're good. So I'm going to redraw the diagram as a P and Q. Right? Think about we got one here and then we got one here. Okay. So the stronger one is actually going to be S and then G phi. So this is like a stronger filter. There will be fewer models that can satisfy this. And then we got another one, which will be the right-hand side. S satisfy FG phi. And we are saying that not vice versa, right? Because we will be able to find some model here. So this can be a path or a model, a path that satisfies FG phi but not G phi, right? And you can think about for that particular model you choose, for that particular witness you're choosing exactly like this. Okay? So that would be the witness. Okay, I think that we actually covered quite a bit today, just about different techniques you can use. So later on, we're going to go over maybe 2 more patterns on Wednesday. And then later on, if I give you a new pattern, you will know exactly how to get its formal meaning. All right, thank you so much. I'll see you on Wednesday.